Hello students, so continuing with the applications of Gauss theorem, in this episode we will discuss another application, and here we will try to find an expression for the electric field at a point due to an infinite plane sheet of charge. So what we will do is we will consider a sheet where charge is uniformly distributed over its area. So it is but obvious that it is a two-dimensional case, right? So this is suppose an infinite plane sheet. This is an infinite plane sheet where charge is uniformly distributed over its area. Let's consider a small portion of this infinitesimally plane sheet of charge. So this is the area, small portion under consideration. Say its area is A. Area of only this portion, and in this area A, let charge Q be the charge which is uniformly distributed over this area A. So surface charge density would be given by charge per unit area. So the charge contained on area A would be sigma multiplied by A. And in this case, we are considering the sheet of charge to be of negligible thickness, right? So our objective is to find the electric field at point P due to this infinite plane sheet of charge. Here one thing I would like to mention is that the size of this portion which we have considered is immaterial. Why? Because if you consider a circular section of larger area, then A will increase, charge distributed over it will also increase, so that the ratio always remains constant. So whether you consider a reference circular portion to be of smaller area or greater area, it won't affect into the ultimate result, right? So sigma will remain constant. With the increase in A, Q will increase. With the decrease in A, Q will also decrease. So the ratio, that will always remain constant. Okay, coming back to the article, this is the point where the electric field is to be found due to this plane sheet charge distribution. Again, we have to make use of Gauss's law. For that, Gaussian surface is to be considered. Here also it is convenient or it is advisable to consider a cylindrical Gaussian surface of circular cross section of area A. Like this, I will draw the diagram. And let point P be lying on one of its circular cross section, like this. This is a cylindrical Gaussian surface. This is a sheet, this is a plane sheet, this is observation point P. So we are considering a cylindrical Gaussian surface, half portion lying on this side and half portion of the Gaussian cylindrical surface lying on the other side, right? This is the area. So we are considering a cylindrical Gaussian surface in such a manner that point P lies on its circular cross section. So since this is a right circular Gaussian surface, area would be same as that of this one, right? Also, it has got three faces, two circular faces and the other one is curved one. So let us put the surface as 1, curved surface as 2 and another flat circular surface as 3. What about the area vector of this surface? Small portion, its area vector would be around this direction, ds1 vector. What about the area vector of the second portion? Its curved surface. Area vector is always in the outward direction, ds2. Its angle is 90 degrees. What would the area vector of this third portion, which is again a circular section? So it will be again in the outward direction. This is ds3, right? So let's apply Gauss theorem. There is a Gaussian surface. So Gauss theorem states that electric flux, which is closed surface integral of the electric field, it is given by 1 by epsilon times net charge enclosed by the Gaussian surface. What is the charge enclosed by the cylindrical Gaussian surface? It is Q. We are not bothered about the charge that is outside this Gaussian surface. We are only bothered about the charge which the Gaussian surface encloses, and that is Q. So 1 by epsilon times net charge enclosed. Now this is closed surface integral. It can be divided into three parts. First, second and third. So we can write it like this: E vector dot ds1 vector for the first one, then E vector dot ds2 vector for the second curved surface, and E vector dot ds3 vector again for the circular section, and it is q by epsilon. So let's evaluate it. I have told you flux is contributed only by those electric field lines which crosses normally through a surface. Now look, if you consider this to be a plane sheet of positive charge, electric field would be in the outward direction like this, isn't it? From positive charge, electric field is always in the outward direction. So electric field due to this charge would be along this direction. This is the electric field. Again, on this side the electric field would be again in the outward direction. Over here, electric field is along this direction. So basically electric field would be along the curved surface while perpendicular to the circular cross section, as it's pretty evident from the diagram, right? So these are the two faces through which field lines are crossing normally. So these are the two faces which will contribute towards the flux. While consider the curved surface, here the field lines are directed along the curved surface. So this won't contribute towards the flux. Mathematically it can be justified. Let's consider the first case. The angle between these two is 0 degree. So it will become E ds cos 0 is 1. Integration of ds1, that will give you the total area, plus E dot ds2. This is the direction of the electric field and this is the area vector. So angle is 90. Dot product of any two perpendicular vectors is always 0. Cos 90 is 0. Again, E ds3. The angle between these two is 0 degree. Cos 0 becomes 1. E at any point over here is constant, so it can be taken outside. Integration of ds3, that will give again the area of the circular cross section. So we get EA. It is q by epsilon. Therefore, what we get is twice EA is equal to q by epsilon. Q can be written as sigma A. So AA get cancelled. So electric field is given by sigma divided by 2 epsilon. So this is the expression for the electric field at any arbitrary point due to an infinite plane sheet of charge of negligible thickness. So you can easily judge this expression for electric field is independent of the distance of the observation point R from this plane sheet of charge. So it is constant. It do not depend upon R. So if you plot a graph showing the variation of electric field with distance R, in this case, the graph obtained would be like this. This is electric field, suppose, and this horizontal axis, it represents, suppose, the distance. So electric field is constant, whether you consider the observation point to be over here, anywhere, the expression for the electric field will remain constant, since it is independent of distance smaller, isn't it? So it will be a straight line parallel to the horizontal axis. This is constant, so it will be sigma divided by 2 epsilon. So this is the graph showing variation of electric field E with distance R, right? So this was an important result. We'll discuss special case as well. What we do is, we'll consider a plane sheet of charge of finite thickness. I'll give you an illustration. This is a page. Suppose this is a page. This is of negligible thickness. If charge is distributed over here, then we have already dealt with this case. Means when the charge is uniformly distributed over a plane sheet of charge of negligible thickness. Right? In this case, what happens is, in this case, the same charge, suppose this is the charge, same charge would appear on both the faces, on this face as well as on this face. The same charge Q would appear on both the faces of the conductor or on the surface of this plane sheet. This is in the case when we consider the thickness to be negligible. Now consider this case. Now it's again a plane sheet but of finite thickness. In this case, charge Q would be distributed over area 2A. This area is A, this area is A. So that will be the only difference. In case of negligible thickness, like in this case, same charge Q would show up on both the faces. But in case we consider a plane sheet of charge of finite thickness, then charge Q would be distributed uniformly over area 2A. Area 2A, one on this side and the other on the other side. So total area would be 2A on which charge Q will be uniformly distributed. Right? So let's deal with that case of finite thickness. This is a special case. In the earlier case, we have considered the plane sheet of charge to be of negligible thickness. But it is a special case which we are presently dealing with. In this case, we will consider the plane sheet of charge to be of finite thickness. So let's modify the diagram somewhat. It will be like this. Thus it will give you a three-dimensional appearance. So this is of finite thickness. Just now I have explained. In this case, charge Q will be distributed uniformly over area 2A on both sides of the conductor, on both sides of the surface of the plane sheet. So it should be somewhat like this. Okay, this is it. It's of finite thickness. So only difference in this article is charge Q is distributed over area 2A. One on this side and the other on the back side, on either side of the conductor, right? So Q here would become twice sigma A, right? We'll proceed in the same manner. Net electric flux is given by 1 by epsilon times the net charge enclosed. Net charge enclosed in this case will also remain Q. So it can be divided into 3 parts. First, second and third. Only these 2 parts will contribute towards the flux. Curved surface won't contribute anything towards the electric flux. Angle being 90 degree. Electric field and area vector, they are at right angle. So it will become 0. So EA, Q by epsilon. So we get 2A equals to Q by epsilon, right? Q by epsilon. Now, if you substitute the value of Q over here, 2EA is equal to, substitute this value of Q over here. So it is twice sigma A divided by epsilon. So 2A get cancelled. So E would be equal to sigma by epsilon. Here also the electric field is constant. It is independent of the distance of the observation point. But in this case, electric field is given by sigma by epsilon. So the graph will remain same. Only thing is the constant value of electric field at any point would be sigma by epsilon. So this is a very important point to be noted down. So in case of any numerical, you need to consider this aspect. I'll repeat this observation. Look, for an infinite plane sheet of charge of negligible thickness, the electric field is given by sigma by 2 epsilon. And in case of an infinite plane sheet of charge having finite thickness, the electric field is given by sigma by epsilon. So please do remember these 2 formulas, right? There are several other cases as well. There are certain sub cases which we will discuss right now. So let's consider this case of negligible thickness. The electric field is sigma by twice epsilon. Okay. So our article is to determine the electric field in a region due to 2 infinite plane sheet of charge which are placed parallel and both are of negligible thickness, like this. first sheet and this is the second sheet. Both are of negligible thickness, right? Suppose its surface charge density is sigma 1 and let us consider its surface charge density to be sigma 2. So, the special case is we need to determine the electric field in these three regions due to the two parallel infinite plane sheet of charge of negligible thickness. So what we do is consider simply this case, only consider first case. Due to this first sheet, you are aware electric field, since it is positive charge, it will be in the outward direction. It will be in the outward direction. So let's draw the vector diagram. This is it. This is E1 over here and this is also E1. And here it will be in the outward direction like this. Due to a positive plane sheet of charge, the electric field would be in the outward direction. Right? We are considering positive charge. And the magnitude would be equal since it is independent of the distance of the observation point. Now consider the second one, second plane sheet of charge. Due to this again, the electric field would be in the outward direction. So let us represent the electric field due to this sheet by E2. So it will be along this direction. This is E2. Right? E1 is the electric field in these three regions due to first sheet. E2 is the electric field in these three regions due to this second sheet. Strength or magnitude of the electric field E1 would be sigma 1 over 2 epsilon, while the strength of E2 would be sigma 2 by twice epsilon. Is that clear? Now what to do is, suppose these two plane sheets has divided the entire space into three regions, A, B and C. Let's find out the electric field at point A. At point A. Net electric field at point A. Now both these vectors are in the same direction. So obviously they will get added up. Now let's take this to be the positive direction and this to be the negative direction. So net electric field in this region would be minus E1 minus E2. So both are of same direction. So substitute this value over here. So what do you get? Minus 1 by 2 epsilon naught sigma 1 plus sigma 2. Right? This is the electric field in this region. In the central region, electric field would be given by, look, it is in the positive direction, it is in the negative direction. This, as per convenience, will consider to be positive. This is negative. So these two vectors being opposite acted, it will be given by plus E1 minus E2. So substituting the value, we get sigma 1 minus sigma 2. And in the third case, again both are in the same direction and in the positive direction, so both will get added up. So net electric field in the region C would be given by plus E1 plus E2. So it will be 1 by 2 epsilon naught sigma 1 plus sigma 2. So these are the expressions for the electric field in region A, B and C respectively. Now there is another subcase. If this is a very important subcase, if sigma 1 is equal to plus sigma and sigma 2 is equal to minus sigma. So we are talking about two parallel infinitely thin plane sheets of charge having equal and opposite surface charge densities, right? So in such a scenario, substitute this value. In region A, we'll get the electric field to be 0. Sigma 1 substituted by plus sigma, sigma 2 substituted by minus sigma. So in region A, the electric field would be 0. It will be minus 1 by 2 epsilon naught sigma minus sigma. So it will be equal to 0. In region B, substitute this value sigma 1 as plus sigma and sigma 2 as minus sigma. Minus minus it will become plus. So it will be twice sigma divided by twice epsilon. So it is sigma by epsilon. and in region C we get again sigma 1 is plus sigma and sigma 2 is minus sigma. We will get 0. So in case these are having equal and opposite surface charge densities, then the electric field of the extreme sections, extreme region would be 0. The electric field will be only in the central region, and that will be given by sigma by epsilon naught. So this is a very, very important concept which we will be making use of in the next chapter of capacitor. So basically, we can derive this result by vector diagram as well. So let's do that alternative method as well. So what we'll consider is, we'll consider two plain sheets of charge of negligible thickness placed parallel to each other and having equal and opposite surface charge densities. These are the two plane sheets, right? I am doing it by some alternative method, the same previous article. So let's draw two-dimensional diagram like this. These are the two sheets placed. So I will represent by straight line. These are the two plane sheets. This is A, this is suppose sheet 1, this is suppose sheet 2. These two sheets, when they are kept parallel to each other and both are of negligible thickness, then it will divide the entire space into three regions: region 1, region 2, region 3. This is region A, this is region B, and this is region C. So they are of equal and opposite surface charge densities. It is of surface charge plus sigma and it is of minus sigma. So it carries charge positive and it will carry the same negative charge. Both will have the same area. So sigma in magnitude would be charge per unit area, right? Let's draw the vector diagram. Now due to the first, the electric field direction, positive charge, so it will be in the outward direction. I am considering the first sheet. It's placed like this. It's having positive charge distributed over here. So due to the first, the electric field would be like this. This is E1. This is E1. It is E1. It will be in the outward direction, away from the positive charge. Consider the second one. It's negative charge. So electric field will be towards the negative charge. Towards the negative charge. So due to this, the electric field is suppose E2. So this is E2. This will be E2. And towards the negative charge. This will be E2. That's fine. Now we are aware E1 is equal to sigma by twice epsilon. E2 in magnitude again sigma by twice epsilon. So magnitude of E1, E2 both are equal. Say E. Therefore, in region A, net electric field is given by what? These two are of equal magnitude, but they are opposite directed. They will cancel out the effect of each other. Both are of equal magnitude, right? Both are of equal magnitude, but being opposite directed, they will get cancelled out. In region B, net electric field would be, both are in the same direction. Both are of equal magnitude. So the net electric field will be given by E1 plus E2. Both are of same magnitude, so it will become twice E. So it is twice E is sigma by 2 epsilon. So we will get sigma by epsilon. In the third case, extreme region, net electric field would be again given by opposite directed. Both are of equal magnitude and being opposite directed, they will cancel out. So net electric field is 0. So you can prove this article either in the previous manner or in this particular manner by drawing the